The authors propose a progressive domain adaptation framework for thermal infrared (TIR) tracking, known as PDAT, to address the domain shift issue between TIR and RGB datasets. Due to the lack of large-scale labeled TIR training datasets, most existing TIR trackers are trained directly on RGB datasets, resulting in a significant performance drop-off in TIR data. The PDAT framework leverages large-scale labeled RGB datasets to learn tracking universal priors and transfer them to TIR tracking using unlabeled TIR data. The authors first introduce an adversarial-based global domain adaptation module to reduce the domain gap on the feature level coarsely. Then, they design a clustering-based subdomain adaptation method to further align the feature distributions of the RGB and TIR datasets finely. These two domain adaptation modules progressively eliminate the discrepancy between the two domains, enabling the learning of domain-invariant fine-grained features through progressive training. The authors also collect a large-scale TIR dataset with over 1.48 million unlabeled TIR images for training the proposed domain adaptation framework. Experimental results on 5 TIR tracking benchmarks demonstrate that the proposed method achieves a nearly 6% success rate improvement. The paper highlights the challenges of TIR tracking, including low resolution, lack of rich texture details, and low signal-to-noise ratio. Early TIR tracking methods focus on extracting discriminative features, while recent works utilize deep features. However, most existing TIR tracking methods are trained on RGB datasets, resulting in a performance drop-off due to the domain shift problem. The authors visualize the feature distribution of the baseline and the proposed progressive domain adaptation model using TSNE, demonstrating that the distance between the feature distributions of similar samples in different domains is significantly reduced after using the global domain adaptation and subdomain adaptation modules. The proposed progressive domain adaptation TIR tracking framework, PDAT, is a novel approach that integrates segment-anything model-based data preprocessing, adversarial-based global domain adaptation, and clustering-based subdomain adaptation to align feature distributions of TIR and RGB datasets. This framework aims to achieve fine-grained feature transfer for TIR tracking tasks. By leveraging segment-anything model-based data preprocessing, PDAT generates a large number of pseudo-labeled TIR training data, enabling the creation of a large-scale unlabeled TIR dataset. The framework's adversarial-based global domain adaptation module roughly narrows the feature distribution of the overall TIR and RGB domains, while the clustering-based subdomain adaptation module aligns features in the subdomain with similar categories to obtain more fine-grained feature transfer. This hierarchical adaptation approach enables PDAT to effectively bridge the domain gap between TIR and RGB datasets. In the context of deep TIR trackers, related work can be categorized into pre-trained, training from scratch, and fine-tuning based on different training strategies. The authors highlight their contributions, including proposing the first domain adaptation framework specifically designed for TIR tracking, introducing adversarial-based global domain adaptation and clustering-based subdomain adaptation modules, and achieving favorable performance on 5 TIR tracking benchmarks. The PDAT framework demonstrates its effectiveness in addressing the challenges of TIR tracking, where existing methods often struggle to generalize across different domains. Thermal infrared object tracking is a crucial task in various applications, including surveillance and autonomous driving. However, the lack of large-scale labeled thermal infrared training data hinders its development. To address this limitation, a domain adaptation framework is proposed to transfer knowledge from RGB datasets to thermal infrared tracking. The framework consists of 3 core components: segment-anything model-based data preprocessing, adversarial-based global domain adaptation, and clustering-based subdomain adaptation. In data preprocessing, a large-scale unlabeled thermal infrared training dataset is constructed, and the segment-anything model is utilized to generate pseudo-label pairs. This process significantly reduces preprocessing time and increases the dataset size. The global domain adaptation component introduces a global domain feature alignment network that employs an adversarial learning approach. This network utilizes a transformer-based style discriminator to capture global dependencies, enabling the feature model to discern stylistic nuances of input images. The goal is to learn a domain-invariant feature that is not sensitive to image style, effectively transferring tracking priors learned in RGB images to thermal infrared tracking. The limitations of existing thermal infrared tracking datasets are discussed, highlighting the significance of domain adaptation theory in computer vision. The proposed Progressive Domain Adaptation framework offers a promising solution to bridge the gap between thermal infrared and RGB tracking, enabling the development of robust and accurate thermal infrared object tracking systems. The authors compared three pseudo-label generation preprocessing methods in Figure 3, demonstrating the superiority of the style-aware margin (SAM)-based method in generating sample pairs with higher diversity. To achieve effective domain adaptation, they propose a style discriminator that captures the global dependence among features, enhancing the discrimination of stylistic attributes between source and target domains. This discriminator consists of a gradient reversal layer, GRL, and two transformer layers, formulated as equation 1. The training losses for the generator and discriminator are defined in equations 2 and 3, respectively, using a generative adversarial training method. However, the authors argue that global domain adaptation is insufficient for tracking tasks, as it may cause feature distributions of different classes to be coupled. To address this, they propose a clustering-based subdomain adaptation network for fine-grained feature alignment. This involves dividing data into multiple similar subcategories and performing domain alignment on these subcategories. Inspired by local maximum mean discrepancy, LMMD, the authors design an online clustering approach to obtain pseudo-class labels for subdomain adaptation. This involves cross-correlation operations on template and search image features, followed by k-means clustering to obtain C-clusters as pseudo-labels. A voting selection mechanism is introduced to determine the final class pseudo-label, as the clustering results from each stage have a significant impact on tracking results. This approach enables the model to adapt to diverse subdomains and improve tracking performance by aligning features at a fine-grained level. A comprehensive evaluation of the proposed PDAT method for thermal infrared (TIR) tracking is presented, comparing its performance to state-of-the-art trackers on 4 datasets. The results, summarized in the table, demonstrate that PDAT achieves the highest success rate, precision, and normalized precision across all datasets, outperforming existing trackers. The progressive training strategy employed for global and subdomain adaptation is a key factor in the proposed method's success. This strategy involves a 2-stage process, where the global domain adaptation module is first trained, followed by fine-tuning of the subdomain adaptation module. This approach enables faster alignment results and improves the convergence speed of global domain adaptation. Implementation details reveal that the proposed method was trained on 4 NVIDIA RTX A4000 GPUs using the PyTorch framework. The baseline tracker, SIAM-CAR, was used as a reference, and the discriminator was optimized using the Atom optimizer with a poly-learning rate policy. The subdomain adaptation alignment loss is formulated as a combination of category weights and kernel functions for both the source and target domains. This loss function aims to minimize the discrepancy between features from different domains, ensuring effective alignment. The proposed method's superior performance in TIR tracking tasks is attributed to its global and subdomain adaptation strategies. The results demonstrate the effectiveness of the progressive training strategy and the subdomain adaptation alignment loss function in achieving improved tracking accuracy. The proposed method's ability to adapt to different domains and minimize feature discrepancies makes it a valuable contribution to the field of TIR tracking. The proposed method, PDAT, significantly outperforms the baseline tracker SIAM-CAR in TIR tracking, achieving an absolute gain of over 6% and 5% in precision and success rate, respectively. This comparison with other top performance trackers on 5 datasets, including LSOTB-TIR 100, LSOTB-TIR 120, PTB-TIR, VOT-TIR 2017, and VTUAV, demonstrates the effectiveness of the domain adaptation framework in transferring useful knowledge learned in RGB datasets to TIR tracking. The results highlight the potential of PDAT-CAR for enhancing TIR tracking performance, particularly in scenarios with thermal crossover, motion blur, and background clutter. The proposed method, PDAT-CAR, is evaluated on several thermal infrared (TIR) tracking datasets, including LSOTB-TIR 100, LSOTB-TIR 120, PTB-TIR, and VOT-TIR 2017. The results demonstrate that PDAT-CAR achieves state-of-the-art performance on these datasets, outperforming existing trackers such as DIMP and SIAM-CAR. A qualitative comparison between PDAT-CAR and several state-of-the-art trackers on the LSOTB-TIR 100 dataset shows the ability of PDAT-CAR to accurately track targets in the presence of similar distractors and background clutter. A comparison of the confidence maps generated by PDAT-CAR and SIAM-CAR on several challenging sequences of LSOTB-TIR 120 demonstrates that PDAT-CAR significantly reduces interference from background clutter and similar distractors. The results on LSOTB-TIR 120 indicate that PDAT-CAR achieves the best normalized precision and the second best success rate, outperforming transformer-based methods such as CSWINTT and Mixformer. GradCam visualization highlights the ability of PDAT-CAR to accurately identify and locate the target, even in the presence of similar targets or background. PDAT-CAR also demonstrates excellent performance on the PTB-TIR and VOT-TIR 2017 datasets, achieving the second-best success rate on PTB-TIR and the second-best EAO on VOT-TIR 2017. A comparison of several state-of-the-art trackers on the PTB-TIR dataset in terms of attributes shows the significant improvements of PDAT-CAR over SIAM-CAR, particularly in deformation and background clutter. PDAT-CAR achieves significant enhancements compared to the benchmark SIAM-CAR on the VOT-TIR 2017 dataset, demonstrating the generalizability and good domain transfer capability of PDAT-CAR, as well as its robustness for different scenarios. The learned domain-invariant feature can be well adapted to TIR tracking, achieving fine-grained features transfer. The proposed domain adaptation method can effectively address the domain shift problem, which has a huge impact on tracking performance. The proposed PDAT-CAR method demonstrates superior performance compared to state-of-the-art trackers on the PTB-TIR dataset, as shown in Figure 7. By achieving fine-grained feature transfer, the benchmark is elevated from the second to last score to the second highest score. In the VTUA versus dataset, PDAT-CAR obtains the second best performance in both mean success rate, MSR, and mean precision rate, MPR, with a 7.4% improvement in MSR and a 7.3% improvement in MPR over the baseline. This significant enhancement in recognition capabilities for small target objects is attributed to the excellent domain transfer efficacy and robustness of the proposed method. To demonstrate the effectiveness of each component of PDAT-CAR, an ablation study is conducted, focusing on the network architectures. The original baseline SIAM-CAR is compared to variations of the network architecture, with improvements relative to the baseline indicated in parentheses. The results, shown in Table V, reveal that the SAMBASED data preprocessing, Global Domain Adaptation Module, AGDA, and Subdomain Adaptation Module, CSDA, all contribute to the success rate, with increases of 2.2%, 3.6%, and 2.9%, respectively. These findings demonstrate the effectiveness of the proposed global domain adaptation and subdomain adaptation modules, showcasing the significance of each component in enhancing object recognition capabilities. The authors conducted an ablation study on the label selection mechanism in clustering-based subdomain adaptation and the network architecture of PDAT on LSOTB-TIR 100. This involved comparing the proposed PDAT-CAR with other state-of-the-art trackers on the VOT-TIR 2017 dataset. The results, shown in Figure 8, indicate that using the designed label selection mechanism in class pseudolabel generation further improved subdomain adaptation, increasing performance by +2.9% +3.8%. This suggests that more accurate class labels enhance the performance of subdomain alignment. The authors then validated the label selection and alignment way of the subdomain adaptation, as shown in Table V using SAM only as a baseline. The results show that clustering or aligning on the last stage alone yields better subdomain alignment. However, it is unclear whether the alignment or better clustering labels are responsible for this improvement. To address this, the authors fixed the clustering at stage 4 and then aligned the subdomain on all stages, as shown in the fourth row of Table V. The results reveal a significant drop in performance, indicating that alignment on the last stage is critical for subdomain adaptation in this framework. Fixing the alignment on stage 4 and using a simple weighted voting mechanism on pseudoclass label selection of stage 1 to stage 4 yielded significantly improved results, with a success rate increase of +0.7% +1.6% compared to using only the last stage of pseudolabel. This demonstrates the effectiveness of the proposed label selection mechanism in obtaining more accurate pseudolabels for fine-grained subdomain adaptation. A comparison of 3 preprocessing methods on 2 benchmarks, shown in Table 7, reveals that the SAM-BASED preprocessing method achieves the best performance on both datasets. The authors attribute this to the SAM model's ability to segment more diverse and accurate pseudolabel training samples, which is crucial for training the proposed domain adaptation tracking framework. Compared to the recognition-based method, the SAM-BASED method gains a 3.6% and 4.2% success rate on the 2 datasets, respectively. This is due to the recognition-based method generating the fewest pseudo-training samples, which is insufficient for training the proposed framework. In contrast, the detection-based method achieves significant improvement on both datasets compared to the recognition-based method, as the detection model can obtain more training samples with more accurate pseudolabels. This paper introduces an unsupervised dual-level domain adaptation framework for thermal infrared (TIR) tracking, aligning RGB and TIR domains on both feature and semantic levels. It addresses the negative transfer problem by utilizing a partial domain adaptation network, which incorporates sample-level feature reweighting and channel-level feature selection to enhance similar samples and filter unshared features. The authors demonstrate that self-supervised selection of similar samples and features for domain alignment is crucial for tracking tasks where both source and target domains lack class labels. The paper compares 3 proposed preprocessing methods on 2 benchmarks, showcasing that more training samples and accurate labels significantly improve the transfer effect and tracking performance. It also presents the largest scale unlabeled TIR dataset to date, useful for unsupervised and self-supervised TIR tracking. A comprehensive review of existing research in thermal infrared target tracking is provided, citing various studies on domain adaptation, feature learning, and object tracking. The authors highlight the significance of their proposed method, which addresses the challenges of tracking in TIR imagery without class labels. Table 7 compares the performance of the 3 proposed preprocessing methods on 2 benchmarks, demonstrating the effectiveness of the SAM-BASED method.